Okay, so this is problem 27 from chapter 28. So 28, sorry, the other way around. 27-28. So here we have some uniform magnetic field. It's towards right. And we have a particle that enters this field in the plane that makes an angle of 45 degrees. Right? And we are asked to determine certain parameters about this motion. The motion itself is in fact given. This is going to do some helical motion around the magnetic field lines. And we are required to calculate, so let's draw the roughly. The figure in the book is much better. We are required to find the so-called pitch distance as it passes through to minimal values, or we could also look at the pass-through to maximal values. Okay? And we are given that this is an electron, so we know the mass and the charge. And we are given the strength of the magnetic field. And we are also given, I think, its velocity. Yeah, that's its speed. All right. So this is a conceptual example from the book that this leads to some helical motion. Now, how would you actually visualize this? How would you go about finding that this is in fact helical motion? Now, one way to do this is to decompose this velocity into two components. Right? So this velocity is going to have some parallel component and some perpendicular component. Okay? So parallel to what? Parallel to the magnetic field. And this is perpendicular to the magnetic field. Now, why do we do this? Why do we do this? Because this magnetic field is going to apply a force, right? And this force, the direction, the magnitude, and it depends on a lot of things, but it is going to be perpendicular to the magnetic field itself. A magnetic force is always going to be perpendicular to the magnetic field itself, which means that it has to be in the plane that's perpendicular to the plane of this blackboard. So it's going to be something in a plane that's perpendicular to the magnetic field, right? So something like this. So then this velocity is going to have two components. One component is in that plane. That is going to feel a force that is going to be affected by the magnetic field. The other one is going to be parallel to the magnetic field, perpendicular to that one. That's not going to be affected by the magnetic field. Okay, so if I decompose this into two components, it does make sense to decompose the velocity into components, because one of them gets affected by the magnetic field. Because of the nature of the magnetic force, it always has to be perpendicular to the magnetic field. The other one does not get affected and just remains constant throughout the motion. So this is somewhat similar to projectile motion, where we decompose this into two motions. One is constant acceleration, it gets affected by gravity. The other one is constant velocity motion, which does not get affected by gravity. Right? But these, of course, happen simultaneously, and we can use the relationship between these two to answer some of the questions. The same deal here. Okay? So these do not happen independently of each other, but the effects are independent. So one component gets affected by B, the other component does not get affected by B. So we are going to have constant velocity motion in this direction on top of some accelerated motion, some circular motion over there. So this is one way. The other way to look at this is to imagine that you have some velocity that's equal to the parallel component of this velocity over here. Right? So you're walking along with this particle. Now what would happen then? For you, the particle would have only a velocity that's now perpendicular to the magnetic field. You canceled out the parallel component. And you know what happens in that case? It's just circular motion. Okay, so if you're moving in this direction, what you're going to see is circular motion by this particle. But somebody else is going to see circular motion that's moving along with you, which leads to helical motion. Okay? So this is another equivalent way to think about this problem. Okay? But the key point here that you should take away from all this discussion is that it's only the perpendicular component of velocity that's responsible for the circular motion. That's the parallel component is just constant velocity motion. It doesn't do anything. All right, so let's write down these equations. What are they asking? Are they asking for the, yes, they're asking for the radius and the pitch. So this magnetic field is going to lead to some force Q be perpendicular times B. That's the magnetic force. This is going to be mv perpendicular square divided by r. This is the centripetal force, right? So the magnetic force is responsible for the circular motion, and we know everything here. We know the charge of the electron, we know the mass of the electron, magnetic field is given. We can calculate the perpendicular components, so in fact these are both equal to v square root of 2 by 2, because the angle is, is 45 degrees. We know this, and we can just calculate everything. In fact, there's some little cancellation happening here. R is going to be m v perpendicular divided by q times p. Okay? Then in the second part, they are asking for this pitch distance. So this pitch distance is the distance it travels along the magnetic field as it goes around in one circle. So we need to calculate the period of the circle and then multiply it by the parallel component of velocity to calculate this distance that it travels as it goes around in one circle. So the period is going to be the circumference, 2 pi r, divided by the velocity. So that's going to be vt. So the magnitude, the direction of this velocity changes, but the magnitude does not change. And so the pitch distance is t times v parallel, and this t is 2 pi r divided by vt. So this is 2 pi m over qb times v parallel, which is just v times square root of 2 divided by 2. Okay? So this will be the pitch distance that will take place for this kind of motion. Right? And I think that's all that they're asking in this problem.